Hi everyone, and welcome to EET1011 one more time. This lecture is for chapter 10 of our textbook, and it's about network theorems. In this first lecture of chapter 10 we will cover sections 1 through 4, and we will have another another video that will cover sections 5 through 9. Okay, so in this first lecture we're going to cover the topic of superposition theorem and Thevenin's theorem. So the superposition theorem extends the use of Ohm's law to circuits with multiple sources. In other words, we're going to apply the same knowledge that we already have about Ohm's law, but we're going to analyze circuits that have more than one voltage source. So in order to apply the superposition theorem to a network or circuit, certain conditions must be met. Okay? Condition number 1, all the components must be linear components, meaning that the current is proportional to the applied voltage. When I say the current is proportional to the applied voltage, so it means that as the voltage goes up, the current goes up, and voltage goes down, current goes down as well. Second condition will be that all components must be bilateral, meaning that the current is the same amount for opposite polarities of the source voltage. Condition 3 is that only passive components may be used when analyzing a circuit using the superposition theorem. These components are resistors, capacitors, and inductors, and they do not amplify or rectify voltages. And fourth condition would be that active components may not be used. In other words, if we're going to use superposition theorem to solve a problem, we cannot use active components in a circuit. Active components are components such as transistors, semiconductor diodes, and electron tubes. These components would be covered in a different course, not in this course, EET1011. And so in a linear bilateral network that has more than one source, the current or voltage in any part of the network can be found by adding algebraically the effect of each source separately. This means that if we have a circuit that has more than one source, let's say a source of voltage, but we're going to analyze the circuit using only one source at a time and see what's the effect of that source on the circuit, and then we're going to add the different results to find the total effect that all sources may have on a circuit. So this analysis is done by shorting each voltage source in turn, meaning that if we have multiple voltage sources on the circuit, we will eliminate the source by putting a straight line through it. And if we have a current source, then we will remove the source, like if we have a open circuit. So here's an example. On this figure we have figure A, and we have two sources. We have a voltage source on top of 24 volts. We have a voltage source in the bottom that is a negative voltage. This is negative 9 volts. And as you can see, they both are connected to ground. So the voltage at the point P right here is 13 volts. So if we have a circuit that has 24 volts here, has a resistor of 30 kilo ohms, another resistor of 60 kilo ohms, and then we have in the other end we have a voltage source that provides negative 9 volts. So we can say that the voltage right at this point, right here, from this point to ground, we can measure 13 volts. How we do this? It's by doing the analysis by eliminating one source at a time. So we have two sources. So the first part, we can eliminate this V2 and connect this basically a straight line from here, like a short circuit. Okay, we short this source like this and connect it directly to ground. Now we have a circuit that has only the two resistors and the one voltage source of 24 volts. So if we apply the voltage divider rule, we can determine that at this point right here, the voltage is 16 volts. Out of these 24 volts, 8 volts I'm sorry, 8 volts are used on the R2, and then 16 volts will be left to apply from here to ground, which is the same voltage at this point. Or we can just remember that if we have this type of circuit right here, we have a voltage source and two resistors in series. To find the voltage here, we can say that this is going to be R1 divided by RT, and then multiply by V1 in this case, okay? And this will give us the voltage at this point P of 16 volts. Similarly, to do the second part of the problem, in this case we're going to eliminate the 24 volts and do a short circuit right here, connect it to ground, and we're gonna utilize now the second voltage source, V2. So if we analyze now the circuit from this point down this way, we can say that in this case the voltage at point P will be R2, okay, R2 divided by RT times negative 9 volts, and this will give us a total of 3 volts. Okay, so the total circuit has two sources, so we eliminate the source 2 and analyze the circuit and calculate the voltage at point P using only source 1. Then we eliminate the source 1 by doing a short circuit like this and utilizing only the source 2 to calculate the voltage at this point again, and now we have 16 volts and negative 3 volts respectively. So on the original circuit, this right here, the voltage here will be the sum of the two voltages calculated utilizing one source at a time. Okay, so 16 plus negative 3, that will be 13 volts, which is the voltage that we say that we had at point P. Here is another example on how to utilize the superposition theorem. This is our original circuit. We have a source of 15 volts, resistor 1, resistor 2, resistor 3, and we have another source on this on the right side of 13 volts. This is V2, that's V1. So the first, we're going to eliminate V2. So what we do is we just do a short circuit right here, and then we'll represent that with a straight line like that, and then analyze this circuit, okay, utilizing V1 only. So as you can see, this R2 and R3 are in parallel, and then whatever we get out of that will be in series with R1. So solving for the equivalent resistance of this circuit would be 106.7 ohms. So if we have that, then we divide 15 by the equivalent resistance, and that gives us the current. Okay, so this would be the total current. That would be the current that comes in here, right? So, and then we also calculate that the current I3 IR3, which is the current that goes in here, so it would be a fraction of that one, so that would be 0.094 amps. So this is the voltage, this is the total current, and this current will split at this point. Some goes this way and some goes that way. Okay, so this is the current. I total current. If I multiply this times 100, that will give me like 14.1 volts on this resistor number 1. Now, if I subtract that from 15 volts, I will get only 0.9 of a volt going through this resistor right here, and multiply this times the current. That will give me a divide that by the current will be 0.094 amps. That would be the current that goes through this resistor. Okay, so, and then once I already eliminated that one, okay, now we're going to eliminate the first source, V1, and calculate the same items utilizing V2. So the equivalent resistance will be 29.09, and that's after we do R1 and R3 in parallel, and then whatever we get out of that is in series with R2, and that total resistance will be 29.09 ohms. So the total current, meaning the current in this direction from the source, would be the voltage divided by the resistance, and that will give you 0.447 amps. Okay, so if that's the case, then multiply this current times the 20 ohms, you're gonna get a voltage, and then that voltage, subtract that from the 13 voltage, and that would be the volts that are consumed on this resistor right here. So divide that voltage by 10, and you get 0.406 amps going through resistor 3. So now we have the equivalent resistance, we have the total current, and we have the current on resistor 3 in two different versions, when we utilize the source 1 and when we utilize the source 2. So at the end, we take both results and we add them together. So here are the results with source 2, and here are the results with source 1. Okay, with V2 and V1, and then adding the currents give you the R3. R3 is going to be 0.5 amps. Okay, because you have that one from when we analyze the circuit with V1, and this one when we analyze the circuit with V2. So we add this plus that one, and you get 0.5 amperes. Okay, so the bottom line of the circuit would be that when we have more than one source on a circuit, we can analyze the circuit by eliminating all the sources except for one, and analyze the circuit with only one source at a time. And at the end, we add the results to get the actual results, okay, the actual answer to the problems. So with a 0.5 ampere flowing in R3, that means this resistor right here, we know now that the current flowing through here is 0.5 amp. So the voltage across R must be 5 volts, because the resistance is 10 ohms. So 10 ohms times 5 amps, that will give you 5 volts. Using Ohm's law, we learned that like back in chapter 2 or chapter 3. So the voltage across R1 must be, therefore, the 10 volts must be at 10 volts. Okay, because using KVL. So if this is 15 and we are utilizing 5 here, so out of the 15, 5 goes to here, so 10 must go to R1. So, and the voltage on R2 will be 8, because we have a total on this, in this loop right here, we have a total of 13 volts. But now we already know that R3 is consuming 5 volts. So 5 volts are dropped across R3, so 13 minus 5, that will leave you that will leave you a total of 8 volts to be drop over the resistor 2. So solving for the current in R1 and R2, we will verify that the solution agrees with KCL. So if I already know the voltage and I know the resistance, so the 8 divided by 20, that would be 0.4 amp. And in here we know that the voltage across this resistor was 10 volts. So 10 divided by 100, that will be 0.1 amp. Okay, so that would be 0.1 amp would be the current 1 in this loop, or this direction if you want, or this direction right here. So current 1 would be 0.1, current 2 would be 0.4. The current on resistor 3 would be the sum of these two currents because they're going in the same direction. Okay, so it would be I1 plus I2, and that would give you 0.5 amp, which agrees with the result that we got from analyzing the circuit through the superposition theorem. Okay, now we get into the Thevenin's theorem. So we're gonna take a break, and when we come back, we're going to analyze the section 10.2.